Okay, we're now going to run the experiment of rossby waves. So once again, let's go in the example directory, shallow 2D. We're going to go in the MATLAB directory, and we're going to look at the grid and initial condition. And in particular, in the grid file, we're going to enable a change in the f parameter as a function of latitude. And oops, sorry. And this is at the end of this file where we define, we change the grid file here. So ncf, which is the f parameter, instead of being just equal to f naught at this point, it's going to be equal to f naught plus a beta y, which is basically where beta is the beta parameter, which is df dy, which is meaning there's a latitudinal gradient in f. So I'm going to comment this one out, and we're still going to keep a flat bottom. Okay, so I'm going to save that. The other thing that I'm going to do is I'm going to change the initial condition and put the bump now in the middle of the domain again. And so here I've uncommented this line that places the sea surface height bump in the middle of the domain, dx over 2. And I'm going to comment out the one that we use for the Kelvin wave, where the bump was at the eastern boundary. So I'm going to close that. I'm going to run MATLAB. I'm going to, just run the creation of the grid and also the creation of the initial condition. So you can see here there's some output here which tells you the average time it takes for a wave to propagate across the domain. It also tells you the long rossby waves take about 15 days and so forth. Okay, so with that in mind, then I'm going to run the model and using the script run model PBS, which I already shown you how to do that. And once the model is finished, I'm going to move the history files in the output directory. Okay, this history file here, I'm going to move it into his underscore beta.nc. Okay, I will do this for both the history file and for the average file. And since I've already performed these runs, you can, if you do an ls, these runs are already there. And also the average file beta. Okay, and I decided to call them beta simply because I'm enabling the beta parameter, but you can call them whatever you want. Now whatever name you call it, then you can plot these using this plot rossby wave function, which I invite you to again study very well all these plotting functions. And so here, for example, you put the name of the history and average files that you want to use for the plot, and then you can just execute this. But again, study these things because all these plotting functions are things that you should learn and are very handy. So let's look at the rossby wave. And first we're going to look at the fast part of the solution, okay, the transients, so in the early days. And let's press return here. And if we look at the interior, again, we found the bump. And from the bump, we have this radiation of inertial gravity waves. And this is pretty much the same as we saw in the F-plane. And you cannot really distinguish any kind of real rossby wave propagating towards the west, say in this particular solution. So this is like 3 or 4 days, and of course the rossby wave takes a little bit longer than that. Okay, so at this point, by pressing return again, we can look at the slow evolving component, which is the solution from the average file. And here you can see the bump a little bit better, and you can see the bump, it's propagating, and after about 15 days it reaches the boundary here, and you can see that there's a train of bumps of these rossby waves that are moving towards the western boundary. Now at each location of this bump, the flow is approximately in geostrophic balance, but however the bump itself has a slow evolving component, which is this rossby wave, and it propagates towards the west. Okay, in fact, if we now make a plot of a transect along the middle of the domain from west to east as a function of time, which is this next plot here, we should see in fact that these anomalies are moving towards the west. Oops, here we go. So this is our initial bump, and you can see that the bump has been moving towards the west. And in fact, at a later time, you no longer find a bump sitting there, but things have been propagating away. So in other words, the difference from the F-plane is that the bump in the f-plane would geostrophically adjust and stay in place, whether here now there's also a slow evolution of that bump, which is moving with this Rossby wave towards the west, and so the bump is no longer there, and you have all these other solution part. Now you can also see that because of the initial gravity waves, if you look, if the bump originated here, you also have excitement of waves before the bump in the eastern side, and also all the way back to the boundary. So there's this interference effect that excites other Rossby waves that have a Rossby wave component that also propagates. So now towards the end of the integration, you find that there's basically a westward phase propagation apparent all over the domain. Okay. Now we can also look at the final state of the solution, which is plotted now here. And in this case, you find that in the sea surface, in the sea surface, you don't find no longer just one bump in the middle like we did before, but it's all like scattered around, and that's because the Rossby wave has moved towards the west, and then you have other excitations in other locations. And so also for the U bar and V bar, you find that each of these bump has somehow a geostrophic adjustment, is quasi-geostrophic adjustment, but each one of them has its own, and so you don't find any more like just one bump sitting in the middle of the domain. So this is all for the Rossby wave, and we're going to go next and look at the topographic waves, which have similar dynamics as Rossby waves, but now the restoring force, instead of being the changes in the Coriolis parameter as a function of latitude, the restoring force is going to be the sloping topography.